Hello everybody, and welcome to part 3 of our videos on the substitution rule. So we're actually going to start out by talking about the integrals of symmetric functions, and I referenced the even case in a previous example as I quickly did an alternative method. So we're going to talk about that and justify it more carefully here. So suppose f is continuous on the interval from -a to a, including the endpoints. If f is even, that is, f of -x is equal to f of x, then the integral from -a to a of f of x dx is equal to 2 times the integral from 0 to a of f of x dx. All right, well, if f is odd, that is, f of -x is equal to negative f of x, then the integral from -a to a of f of x dx is just 0. So let's take a look at a picture. Actually, I think these are really well explained just by the picture. If we think of what this even property means, it means whether we plug in the negative or positive versions of x, we get the same output. See, we get the symmetry across the y-axis here. So the area all the way from -a to +a would actually just be double the area for one section. So twice the integral from 0 to a of f of x dx. On the other hand, if f is odd, f of -x is equal to negative f of x, then the graph looks like this. Your y values become the opposite when you cross from negative x to positive x values. So these two areas, one gets counted as a positive, and the integral treats the other as a negative and cancels the two out. Okay, well, the picture's good, and I think does a good job explaining it, but let's actually prove this. So we're going to prove this second one. So if f is odd, that is, f of -x equals negative f of x, then the integral from -a to a of f of x dx is 0. Okay, so if I have an integral from -a to a of f of x dx, I can split that integral up to the integral from -a to 0 of f dx and 0 to a of f dx. So on this on the integral from -a to 0, we're going to cleverly do a substitution of u equals -x. Now, that gives us that du equals negative dx, and negative u equals x. So du is negative dx, negative u equals x. Here, all we've done is just moved our negative over, or multiplied both sides by -1. Now, when we evaluate our endpoints, u of -a would just be positive a, and u of 0, when I plug in 0 here, I just get 0. So now when I look at this left-hand part of these two terms, I get -a to 0 of f of x dx is the integral from a to 0 of f of -u times negative du. Now I can take this negative du and put it out in front because that's just multiplication. On the other hand, with the f of -u, this happens because of the odd symmetry. The fact that f of -u is equal to negative f of u. So I can pull out the negative. I shouldn't say pull out because it's not factoring, but the odd symmetry tells me that this f of -u, oh, it looks like there's a little typo here. Glad I caught that. That odd symmetry tells me that I can take f of -u and rewrite it as negative f of u. But a negative of a negative is a positive. So this is the integral from 0 to a of f of u du. Wow, are there two typos here? Sorry about that. Okay, let's try that again. So I use the odd symmetry here to make f of negative u equal to negative f of u, and that canceled this negative out. And now I can use a property from Calc 1 that if we flip the bounds of our integral, the integral becomes negative. So now this is negative the integral from 0 to a of f of u du. Now, of course, these two integrals, if you evaluate them with the fundamental theorem of calculus, they are exactly the same thing. Doesn't matter if we call this u and du and call this x dx. That doesn't change anything. So, in other words, when I take this function here, negative a, this integral here, negative a to a of f of x dx, and I split it up, I can take the integral here, the left-hand part of this sum, and rewrite it as negative the integral from 0 to a of f of x dx. So if I have the negative of this plus the positive of it, I just get 0. Alright, so that's the proof for the odd symmetry. I'm not going to do the proof of the even symmetry here, but it's very, very similar. Okay, so recall cosine of x, secant of x, and any polynomials with only even-powered terms, like 3x to the fourth plus x squared, are all even functions. And sine of x, cosecant of x, tangent of x, cotangent of x, and any polynomials with only odd-powered terms, like 8 times x to the 7th plus 3x to the 3rd, are odd functions. So let's take a look at evaluating an integral here. So one of the things that I see pretty often is that students see an integral like this and they're like, oh my god, that integral is impossible, I don't know how to do it. And then they get confused. Well, if you pay close attention, you notice, oh, I've got negative a to a. Well, whenever you see that with an integral that looks really tough, you should check if it happens to be an odd function. So if I look at f of x equal to sine of x plus x to the 7th times cosine of x. Well, let's check if it's an odd function. If I plug in negative x, what do I get? I get sine of negative x plus negative x to the 7th times cosine of negative x. Now, sine of negative x is negative sine of x because sine of x is an odd function. Now, this is an odd polynomial, so this is also an odd function, so this is negative x to the 7th. But cosine of x is even, so cosine of negative x is negative cosine of x. Or sorry, is positive cosine of x. Let me try that again. Cosine is even, so cosine of negative x is just equal to cosine of x. Now if I factor out a negative 1 from both terms, I get negative sine of x plus x to the 7th times cosine of x. But this is my original function. So this is all just negative f of x. So f of negative x equals negative f of x. That means this is an odd function. And since we've shown it's an odd function that's integrated from negative a to a, it's just 0. That's all we have to do. All right, now let's take a look at this one. Now, this function doesn't look like an odd function, but maybe it's an even function. And in fact, it is an even function. So if I take f of x as secant squared of x plus 4x to the 4th plus 7 all over x squared. Then when I plug in negative x, I'll get secant squared of negative x plus 4 times negative x to the 4th plus 7 all over negative x squared. And each of these functions that we plugged negative x into is an even function. So I can just get rid of the negatives and write this as secant squared of x plus 4x to the 4th plus 7 over x squared, which is of course just equal to f of x. All right, now it's not as easy as the odd function situation. We're still going to have to do some work, but this does cut out some algebra for us and let us rewrite this as 2 times the integral from 0 to 2 of secant squared of x plus 4x to the 4th plus 7 all over x squared dx. Now, I'm not actually going to finish this problem because, well, I'll show you. I just wanted to use this as an example for a setup. Okay, so these two are easy to deal with. This is not. In fact, we don't have any real tools at this level to deal with this kind of thing, so don't even worry about it. But I just wanted to demonstrate checking that this was an even function and applying that property. All right, so let's wrap this up with one proof of another property. So there are a lot of properties that you can use the substitution rule to prove about various functions that we can kind of use as shortcuts in evaluating particular situations. So in this case, the integral, if f is continuous on R, that is the real number line, prove that the integral from a to b of f of x plus c dx is equal to the integral from a plus c to b plus c of f of x dx. So we're going to start out by just making a substitution. We want to get rid of this x plus c. So we're going to let x plus c be equal to u. That would imply that du is equal to just dx. And u evaluated at a is just a plus c. And u evaluated at b is just b plus c, right? We're just plugging b into our function for u. So this implies that the integral from a to b of f of x plus c dx is the same as the integral from a plus c to b plus c of f of u du. Now, by the fundamental theorem of calculus, this is, so well, let me just write this separately. So this is by the substitution rule. So when we're writing proofs, if we use a theorem, we should cite that theorem. We also have that the integral of a plus c to b plus c of little f of u du is equal to cap f of b plus c minus cap f of a plus c, which would also be equal to the integral of from a plus c to b plus c of little f of x dx by the fundamental theorem of calculus. Right, so these two things are totally equal by the fundamental theorem of calculus. Right, the fundamental theorem of calculus doesn't care what the variable you started with is. It cares what is the antiderivative behavior of the function and what are the endpoints of the integral. So these two things are the same. Hence, if the integral from a to b of f of x plus c dx equals this integral of a plus c to b plus c of f of u du, and that equals the integral from a plus c to b plus c of f of x dx. If all three are equal, then the first and third are clearly equal. So that implies that the integral from a to b of f of x plus c dx equals the integral from a plus c to b plus c of f of x dx. Done. All right, so that's the end of that proof, and that's the end of our videos on the substitution rule. Thank you for watching.